Do another round of El Hardware. Okay, timer's going, let's go. Consider FSM with SW input. Assume FSM begins in reset state called A. FSM remains in A as long as S is 0 and moves to B when S is 1. Once in state B, the FSM examines the value of input W in the next 3 clock cycles. So, okay, if W equals 1 in 2 of these 3 cycles, then FSM has to set an input Z to 1 in the following clock cycle. Otherwise, Z has to be 0. So B, and it's 2. And then so FSM continues checking W for the next 3 clock cycles, and so on. The timing diagram below illustrates the required value of Z for different values of W. So once you have S, you start this detection sequence, and given you start this detection sequence, you never get out of it. So S only matters the first time it goes to 1. Synchronous reset, and then we can just have enum of A comma B as your state, next state, and then state is just A, and then n else begin n, state is next state, and then you can do always this case of state, and case if it's A, then an S would bring it to state B, otherwise to an A, and then next state is B, basically. Unless I guess you reset, then yeah, if you reset, then you overwrite this next state and you just listen to A. And then outer reset, so if reset state is A, and then so we're back here anyway, so all right, never mind. So if we're in state B, we start out here, we're at 0, and the next state here is B, so we go to B because of S. So 0, 1, 2, right? 0, because, yeah, state is B, and then B count is 1. So basically next B count is 1, next U count is 2, and I need to, after 2, I need to go back to 0. So actually, so if is 2-bit is 2, then zero, otherwise also 0 actually. cleaner because I know I made a typo in that previous thing. So if state is B and count not this, if count is this, we just reset it, and then if we're state B and not count this, so we just go to 1. So 0, 1, 2, 0, 1, 2, 0, 1, 2, so 0, 1, 2, 0, 1, 2, 0, 1, 2. Okay, so the next thing is we probably have like a streaming thing. And the stream will just be 0 or otherwise we can just take W, and so we take W, then we pop the MSB. So the oldest well, the B count will go 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2 until I guess reset. So but then there's also needs to be a count of W's. So if state is B and W, then it's 1, 1, and then 2 here. So here, 1, 1, and then 2. And here it'd be 1. So this is count 0. This is count 0. So if count is 0, then I'll just propagate whether it's 1 or 0 next cycle. So this is gonna be like 1, and then if it's not 0, meaning it's 1 or 2, then I'll just propagate this previous value of w count plus w. So this So basically, if we're not in state B, we stay in 0. If we're in state B and we're like modulo 3, like here, here, or like here, then we just propagate this w to the next cycle, which actually implies that the w count is 0. And if we are not at 0, which means we're 1 or 2, then we just take whatever our w count was, add it to the w. And that's our w count. And then lastly, we assign our z is when what happens if we reset here in the same cycle? I have no clue. If we're reset, I guess we don't really care about the outputs, to be honest. I'll deal with that if that is an issue. So state equals b, and count is 0, and okay. We can do this by inspection because there's only 5. Actually, no, that's probably easier to do it like this. Let's double check. So 0, the next state will be 0 or 1. 1, it'll be 1 or 4. 2, it'll be 2 or 1. 3, it'll be 1 or 2. 4, it'll be 3 or 1. Lastly, if present state is so we're at state 0, 0, 0, and we have 1, which means we go to 0, 0, 1. Cool. And then we have 1 again, which means we go to 1, 0, 0. In the next cycle, here it's also 1, actually. Submit that. So the state is the same, the state evolution is the same. The only thing that's different, and Z is the same. right? So given some state y, we have the same formula to calculate next state, and z is also just going to be based on this state, which is now called y, and we want to return that, I guess y0 is the 0th bit of the next state. Success. So given a state represented by y, then show a state assigned table, derive a next state expression for y2. Okay. Well, the Verilog part is enum, right? Because 0 maps to A and 1 will map to B, and so on and so forth. So in this way, at least this gives us a very convenient way to do this mapping without having to do like cases like 0, 1, 2, 3, 4, 5, 6, 7. So if it's not W, then go to B, else stay in A. So you see how I can kind of universally use like A to F here, and that's interchangeable with Y because of how these are encoded. That's pretty cool. If it's not B, you can go to C. If it is, if it is W, go to D. This feels like manual depth first search. Zero is F and 1 is A, E. One is D. This is also quite hard to debug. If there's anything wrong, you kind of just have to reread it. And no, that's all. B and then A, C and then D. So 0 W. Four and then W. Reason why is because next state is 2 to 0, but this is map 3 to 1, so that's the tricky trick. So this is 1 hot. Actually, what I have 2 is this one, which is very tricky. So y of 2 is talking about b, so b is actually talking about a going into it. And a is 1 and not w or... No, that's it. So 1, 2, 3, 4, we're talking about D. Oh, this is just 1 and not, okay. So D is just gonna be 1, 2, so 2 and W, 3 and W, 5 and W, Y2 looks okay, Y4 is not great for 2, 0 and W. Two, 0 is this, right? Two, 0 is F and W is 1. A, B, C, D, right? So, oh, I missed this arrow, okay. No weird x to 1 encoding, so that's cool. And then I'll just do the case statement up here because it's easier. And then assign z is when, or e or f. And let's just look at the next state. The next state is basically going to be like this. Good. 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 I'll just skip these two. It's like kind of just doing the same thing over and over. So it's not that educational. Let's maybe look at this. Okay, so it's priority arbiter. So So one way to do this is with blocking. So if R3 I guess I could just do it like this. It doesn't matter. So this is all just saying is like, hey, if we're no, this is actually not. All right, so at every cycle, we just start the next state at A. And as you can see here, if all of these are zeros, then next state just gets propagated here as A. Else, if suppose like 1, 0, 0, then this will be D, and this will be 0, this will be 0, so these D propagates. Likewise, if it's like 1, 1, 0, then this one will overwrite this and we'll go to C instead. And 0 will propagate to C. Likewise, if it's question mark 1, okay, whatever. If it's question mark 1, then it doesn't matter, we'll just go to B. So in this case, B has kind of like the final say or the highest priority, and then that's the state transition for A. And how does B work? B just says, if I'm at B, go to A if not R1. Wait, go to A if not R1, else stay at B. Not R1, go to A, otherwise stay at B, okay. And same thing for C, except it's with R2. So this request goes low, go back to A, otherwise stay at C. This is not really a priority arbiter, I guess, because let's say you have 3 and you keep having 3, then it doesn't matter if R1 wants to request. So it's not like, yeah. Anyway, you get the point. If it's not, go to A. If it is, go to back to D. And then lastly, I need to output G, which is D, C, and B. Great success. Next clock edge or next pod's edge. Huge difference. I don't know. Yeah, I think I'll just save that one for next time. Just because I don't think I could do it in 0 seconds. But it seems like a pretty layered problem where you kind of have to implement one part at a time to build out your solution, which I'll do next time.